Now students, having understood the Yukawa theory for nuclear force, now we move into a very important concept which is relevant in this chapter of nuclear physics, and it is the concept of binding energy. Now let's understand what is this binding energy all about and what it represents and how this concept will be useful in certain analysis and interpretation. Now it is found that the rest mass of stable nucleus of a stable atom is always less than the sum of masses of its constituent nucleons. Now when we say nucleons, it means neutrons and protons. Now the difference is called mass defect and we denote it by delta m. The energy equivalent of delta m, that is delta m c square, is utilized in keeping the nucleons bound together. This energy is known as binding energy. In other words, in order to break the nucleus into its constituent nucleons, an amount of energy equal to this binding energy has to be supplied to the nucleus. The mass defect per nucleon, that is delta m divided by A, is called packing fraction of the nucleus and we represent it by P. Now we have used the two words, that is the binding energy per nucleon, and we are calling it packing fraction and the binding energy itself. So students, the fundamental point is that the mass of stable nucleus of stable atom is always less than the sum of masses of its constituent, and the difference in mass is simply referred as mass defect. Now if we consider a very simple situation, that is we have nucleons, that is neutron and proton, at infinite separation initially, that is the initial configuration, and these neutrons and protons, that is nucleon, come into a configuration and form a nucleus. We find that in this process the energy is released, and this energy release will be the binding energy. That is, when nucleons initially at infinite separation enter into a configuration, enter into an entity known as nucleus, the energy released is simply referred as binding energy. And this energy, which we are referring it as binding energy, is nothing but simply delta m c square, where delta m is the mass defect. In other words, we can say if we supply energy equivalent to binding energy, these nucleons will move to infinite separation. Now let's enter into the calculation of binding energy per nucleon and binding energy. Suppose we have a nucleus of element X having mass number A and atomic number Z. Let's say its mass of the nucleus is capital M, and then the mass defect, that is delta m, will be Z times mass of proton, because number of proton is same as atomic number, plus A minus Z, which is the number of neutron, multiplied by mass of neutron. So this is the sum of masses of its constituent minus the mass of the nucleus. This will give me the mass defect. Now this binding energy will be simply delta mc square. Now if we use atomic masses instead of nuclear masses, the binding energy can be written replacing atomic masses instead of nuclear masses. Now we have the important term, which is binding energy per nucleon. Now the binding energy per nucleon will be obtained simply by dividing binding energy by the mass number. Now when we go for analysis for binding energy per nucleon, we get a graph which is shown on the screen. Now this graph is very useful and it gives a lot of information, and there have been questions in exam based on this graph. Now let's look at this graph which is shown on the screen. Here we see the variation of binding energy per nucleon with mass number. Now a simple analysis shows us, and we can see from the graph, which is very evident, that as mass number is increasing, binding energy per nucleon is increasing, it is becoming maximum and then it is sloping down. That's the general trend that you can see from the graph. Initially it is increasing, in between there are few peaks, and then attains a maximum value and then it slopes down. Now there are many implications of this binding energy per nucleon analysis. Now if we just look at the graph, we find that the elements having atomic weights between 40 to 120 have roughly a constant value of binding energy per nucleon. Also we find that in low mass number region, as the mass number is increasing, binding energy per nucleon is increasing. In between we find there are peaks, and these peaks are due to pairing effect. Now wherever nucleons are paired, there will be extra stability associated with them. Now this parameter of binding energy per nucleon is indication of stability of nucleus, and we see that the binding energy per nucleon for iron, it is maximum, and its binding energy is around 8.89 million electron volt. So iron is the stabilized nuclei. Now the average value of binding energy per nucleon of nuclei having atomic weight less than 40 and greater than 120 is smaller than 8.5 million electron volt. For heavier nuclei, the value of binding energy per nucleon decreases to around 7.5 million electron volt. As I said, you can see there exists a cyclic occurrence of a maximum value of binding energy per nucleon for elements having mass number which is multiple of 4 in the low mass number region. Again I explained, this is due to binding, that is a pairing effect, that is wherever nucleons are paired up, there will be extra stability associated. Now this parameter binding energy per nucleon is taken as an indication of stability of a nucleus. The more the binding energy per nucleon, the more is the stability of nucleus. Now a slight analysis of this graph will tell us that why in low mass number region nuclear fusion is energetically favorable, because when two nuclei, that is lighter nuclei, fuse together, we get a product nuclei which will have a binding energy per nucleon more than the fusing nuclei. Hence in low mass number region nuclear fusion is a favorable process, whereas in high mass number elements we find that if a high mass number element splits up into smaller fragments, and the fragments will have more binding energy per nucleon, and that explains why in high mass number region nuclear fission is a favorable